Hello. We are talking about the giants at the heart of darkness, black holes. The most mysterious, terrifying, yet equally mesmerizing structures in the universe. Cosmic monsters that swallow light, bend time, and push the laws of physics beyond their limits. Since ancient times, humanity's curiosity toward the night sky, combined today with modern telescopes and theories, has revealed that black holes are not merely destructive, they also carry creative power. In this chapter, we journey from the curvatures predicted by relativity to Hawking radiation, from supermassive giants to the information paradox. Black holes are a mystery that challenges not only astronomy but the limits of human intellect itself. Defining darkness. What a black hole is and isn't. Black holes are among the most complex structures in the universe, lying at the heart of unresolved physical questions. They are often depicted as terrifying voids that devour everything around them. But this popular image represents only a fraction of the scientific reality. A black hole is, in fact, a solution in which space-time is extremely warped. A specific consequence of Einstein's general relativity equations. Event horizon. The point even light cannot escape. Black holes are defined by a boundary known as the event horizon. This boundary represents the threshold beyond which even light cannot escape. It is, in a sense, where cause and effect relationships are severed. Whatever happens beyond the event horizon becomes invisible to external observers. In this way, black holes are revolutionary not only in terms of gravity, but also in terms of information theory. Schwarzschild, Kerr, and other types of black holes. Based on solutions to Einstein's equations, there are several types of black holes. Schwarzschild black hole possesses only mass, non-rotating, and uncharged. Kerr black hole has mass and angular momentum, i.e., it rotates. Reissner, Nordstrom, and Kerr-Newman black holes, variants that carry electric charge. These types are connected to the no-hair theorem, which states that black holes do not reveal any information beyond mass, rotation, and charge. Singularity, the point where physics collapses. At the core of a black hole lies the singularity, which general relativity predicts as a point of infinite density and zero volume. However, this definition conflicts with quantum mechanics, where infinities are considered unphysical. This creates a boundary where the fundamental laws of physics cannot reconcile, a clear demonstration of the need for a quantum theory of gravity. Entropy and thermodynamics. Do black holes radiate heat? Thanks to Stephen Hawking's revolutionary work in the 1970s, we now know black holes are not entirely black. Hawking radiation suggests that black holes can lose energy and evaporate due to quantum effects. This implies that black holes behave as thermodynamic systems. Building on this, Hawking and Bekenstein developed a definition of black hole entropy proportional to the surface area of the event horizon. Today, physicists view black holes not just as astronomical objects, but as laboratories where information, entropy, and time itself are tested. Information paradox. Where does lost information go? Hawking radiation predicts that a black hole could eventually evaporate completely. But what happens to the information about the matter that fell in? If the information disappears, it violates the fundamental principles of quantum mechanics, particularly the unitarity principle. This is known as the black hole information paradox and remains unresolved. Some physicists argue that information is preserved at the event horizon, while others propose new frameworks such as the holographic principle. In summary, black holes are not merely remnants of dead stars. They are physical systems where the universe's most fundamental principles are tested. They are cosmic laboratories where space-time geometry collapses, energy radiates at quantum scales, and the fate of information remains an open question. Understanding them means understanding not only the universe, but also the nature of information, time, and reality itself. Einstein's legacy, general relativity, and collapsing. The journey toward understanding black holes began in the early 20th century with Albert Einstein's groundbreaking vision. Introduced in 1915, the general theory of relativity did more than improve upon Newton's laws. It transformed our perception of the universe's very structure, reshaped our understanding of time, and redefined what gravity truly is. According to Einstein, mass and energy do not merely attract each other. They bend and curve the fabric of spacetime itself. This curvature dictates the motion of planets, the behavior of stars, and even the path of light. Spacetime is no longer a silent backdrop. It becomes an active, dynamic player in the cosmic theater. Einstein's field equations and black hole types, explained without formulas. Einstein's field equations, though highly mathematical in their original form, can be summarized as a system that links the geometry of spacetime to the presence of matter and energy. When scientists solve these equations under different physical conditions, they uncover the theoretical blueprints for various kinds of black holes. These include Schwarzschild, black holes, the simplest type, defined only by mass. They neither spin nor carry electric charge. Kerr black holes, rotating black holes shaped by angular momentum. Kerr-Newman, black holes, a more complex form, combining mass, rotation, and electric charge. Each of these solutions introduces distinct features, such as singularities and event horizons, regions where the known laws of physics break down, and the return of any object becomes impossible. Gravitational time dilation, time slowed by gravity. One of the most astonishing predictions of general relativity is the idea that time itself flows differently depending on the strength of gravity. The stronger the gravitational field, the slower time passes. Near a black hole, this effect grows so extreme that to an outside observer, an object falling toward the event horizon appears to slow down endlessly, never fully crossing the threshold. This is not a philosophical abstraction. It is a measurable physical reality. The same principle must be corrected for in systems such as GPS satellites, or else global navigation would accumulate enormous errors. Near a black hole, this distortion becomes monumental. Gravitational lensing, the bending of light. Einstein also predicted that massive objects influence the path of light. Around black holes, this bending becomes so dramatic that it can produce magnified images, arcs, or even perfect rings, now known as Einstein rings. These distortions allow astronomers to detect black holes indirectly and to study galaxies billions of light-years away. Unresolved questions. Paradoxes at the edge of physics. While general relativity predicts the existence of black holes with astonishing precision, it also challenges the foundations of modern physics by introducing unresolved paradoxes. The information paradox. What happens to information swallowed by a black hole? Does it vanish forever? The singularity problem. Does physics simply collapse at the center of a black hole, or do unknown laws emerge at this scale? These questions reveal the need for a unified theory, combining relativity with quantum mechanics, a goal that remains one of the greatest scientific quests of our era. The final dance of mass, stellar death, and black hole formation, supernovae, neutron stars, and collapse processes. One of the universe's most dramatic stages occurs at the end of a massive star's life. This is not merely an ending, but also the origin story of black holes, and mass plays the leading role. A star's fate is determined by its mass from the moment it forms. Low-mass stars evolve into red giants and end as white dwarfs, while massive stars, at least 8 times the mass of the Sun, face a far more dramatic conclusion: core collapse. These stars generate energy through millions of years of nuclear fusion, converting hydrogen into helium, helium into carbon, and eventually heavier elements. However, when the fusion process reaches iron, it stops producing energy. Instead, it consumes energy. The star's internal pressure collapses, unable to counteract gravity. At this moment, one of nature's most violent events occurs: a supernova explosion. The outer layers of the star are ejected into space, while the core continues to collapse. At this point, 2 outcomes are possible. 1. If the core's mass is below a certain threshold, roughly 1.4 to 3 solar masses, a neutron star forms. This is an extremely dense object, where protons and electrons have fused into neutrons. 2. If the core's mass exceeds this limit, no force can counteract gravity. Matter collapses entirely. Density approaches infinity. Volume approaches 0. The result? A black hole is born. From the outside, this collapse may appear as a loss, but in reality, it is a fundamental physical transformation. It is not merely matter changing form. It is the geometry of space-time itself that is redefined. A black hole is the stabilized outcome of this transformation, where the unknown lies beyond the event horizon. It is important to note that the interior dynamics of black holes cannot be directly observed. We can only model these processes based on general relativity and limited quantum theory insights. Yet, these two frameworks clash at the singularity. Black holes thus become theoretical laboratories testing the fundamental laws of the universe. In other words, black hole formation is not just an astronomical event, but also an ontological question. As mass collapses upon itself, the universe's information and structural codes do not resolve. They deepen the mystery. Each black hole is not merely the end of a star, but a new why posed to science itself. Hawking radiation, vapor rising from silence. The connection between quantum physics and black hole evaporation. In 1974, a revolutionary proposal shook the world of physics. A young theoretical physicist at the University of Cambridge heard the voice of quantum theory, where classical physics remained silent. Stephen Hawking went beyond Einstein's relativity laws and the classical understanding of black holes, fundamentally challenging the notion that black holes only absorb. According to him, the darkest structures in the universe were not completely silent. They were slowly and subtly evaporating. According to classical physics, black holes swallow everything irreversibly. Even light cannot escape once it passes the event horizon. However, this view conflicts with quantum field theory and thermodynamics, which suggest that every physical system must have a temperature and entropy. Hawking filled this gap. Black holes actually radiate. This process is known as Hawking radiation. The mechanism relies on quantum uncertainty principles. Near the event horizon, virtual particle-antiparticle pairs constantly form. Normally, these pairs annihilate each other, but if one falls into the black hole, while the other escapes into the universe as a real particle, the black hole loses energy. Slowly, it loses mass, and eventually, it can evaporate entirely. This theory treats black holes as thermodynamic systems. Hawking showed that a black hole's temperature is inversely proportional to its mass. The smaller it is, the hotter it radiates. Massive black holes barely evaporate, while miniature black holes, at least theoretically, can lose energy much more quickly. This opens up the possibility that primordial black holes formed in the early universe might have completely vanished by now. Yet this proposal raised another question. What happens to information? If a black hole evaporates and disappears, what becomes of the information that fell into it? Quantum mechanics asserts that information can never be destroyed. But if Hawking radiation is purely thermal and random, the evaporating black hole seems not to return this information to the universe. This creates a profound conflict, known as the information paradox. Still, one of the greatest unresolved theoretical problems today. Hawking radiation not only deepened our understanding of black holes, but also directly contributed to efforts to unite quantum mechanics with general relativity. Today, many theories, string theory, holographic universe models, quantum gravity approaches, have been developed to understand the nature of this radiation. In this context, Hawking's proposal is not merely a model of emission. It is a compass guiding modern physics toward a unified theory. Under this framework, black holes are no longer absolute destroyers. They interact with the universe, change over time, and are woven with information. And silently, very, very slowly, they evaporate. The curvature of space-time, black hole effects, and the